Hello my friends, and welcome to the last PowerPoint of the course. Today we're going to dive a little bit into how all this ln and e stuff might fit together, not only just for its own sake, but also to tackle some of the hardest problems you will see in calculus. So our story begins with just a basic problem, just to remind you of some of the core skills that you already know. If I'm trying to find f prime, that means I'm looking for a derivative, and if I've got something to the second, I can use the chain rule to say 2 stuff, and then I would say times the derivative of that stuff, which would be 16x, and that's my answer. Then we encountered this one. Now, this is by far the most complicated derivative I've ever shown to you. At first glance, if you're a very conscientious student and you've got a whole lot of time on your hands and this is extremely important to you, you could solve this problem. You see a quotient rule, which would be your first step. To get your u prime, you'd have to do a product rule. Within each one of the branches of that product rule, for your u and for your v, you'd have to do a chain rule on either side. You could put together that monstrous thing and you could get the answer. It does not use any skill you have not already seen before. It would just be a whole lot of writing to try and tackle this problem. We're not going to do it that way. Instead, we're going to talk about how we could use logs and all these things that we've learned about logs in calculus to make this problem a little bit easier. Please note, it's just a little bit easier. Alright, so what we're going to do is we're going to take the natural log of both sides. So the natural log of y, you know what, just to save some space, I'm going to say the natural log of y equals the natural log of all that stuff. So when we split that, the natural log of y just stays natural log of y. But all these things over on the right, I can split up using my log laws. I know that two innards multiplied together in a logarithm becomes the natural log of the first thing plus the natural log of the second thing. And if I divide inside a logarithm, it would be minus the natural log of the bottom. So in the very least, introducing logs makes all the fractions go away. I can actually go a little bit further by saying that this squared inside the log can come out front. In fact, the square root is just a 1/2 power, so I can bring that out front as well, just to try and make the problem a little bit easier. This last guy doesn't have any exponents, so we just leave that as is. Alright, so now we want to use implicit differentiation. Remember, for implicit, anytime you have a y, you take the derivative normally. The derivative of ln is 1 over u, and then I follow that with the derivative of u, so that's y prime. Over here I'd end up with that 2 over 8x squared plus 3, and then I multiply that by the derivative of 8x squared plus 3. This 1/2 I could think about as 1 over 2 times 4x cubed plus 10. Follow that up with the derivative of 4x cubed plus 10 minus 1 over 23x minus 8 times 23. So notice that I didn't need any quotient rules, I didn't need any product rules, and if you're using good logarithmic differentiation, you should not need those rules. At most, you're going to need chain rules just for each piece of the problem. So to get my final answer, I have to remember, I'm not looking for 1 over y prime, I'm just looking for y prime equals. To get y prime by itself, I just multiplied both sides by y. So just as long as I'm going to rewrite this, I might as well combine it. 2 and 16 are going to make 32x. Plus, then I've got 12x squared over 2 is going to be 6x squared. And then that 23 really doesn't combine with anybody. And that's my answer. Side note, if you're doing this in college, some college professors don't really want to see that y in the problem because it kind of feels weird to define y prime in terms of y. So what they might actually ask you to do is take that y out front and replace it with all of this. So you'd actually get this whole monster fraction out front because that's what y equals, and then all this stuff inside the brackets. Alright, so let's try another one. Now again, you have the skills to do this problem. You recognize there's a chain rule. When you go to get your u prime, it's going to involve a quotient rule. You 100% know how to do this. But I want to practice this new ln stuff. So I'm going to think about this as ln of y equals, I'm going to bring that 1/2 out front, ln of x minus, now you got to be a little careful here. It's not just the x that's being square rooted, it's the x plus 1 as well. So when I write the ln of x plus 1, it also gets a 1/2 out front. Alright, so now I'm ready to do calculus. I'll take my derivative, 1 over y prime, equals 1 over 2x. I don't need a chain rule because it's just plain simple x, minus 1 over 2 times x plus 1. Again, I don't need a chain rule because the derivative of x plus 1 is just 1. So going for the big finish, y prime equals y times 1 over 2x minus 1 over 2 times x plus 1. In my personal opinion, that's easier than doing the chain rule and the quotient rule, but it's probably a fairly similar balance. Again, you could, if you wanted to, do a quotient rule. Inside the quotient rule, you'd have a product rule. You could even bring this secant squared up top and do a 3-part chain or a 3-part product rule if you really want. But I'm going to practice this new log stuff. So ln of y equals ln of x plus ln of sine x minus 2 ln of secant x. Alright, so let's break this down. My derivative of ln y is going to be 1 over y prime. My derivative of ln x is just simply 1 over x. My derivative of ln sine is 1 over sine x, but then I've got to multiply that by the derivative of sine. My derivative of sine is going to be cosine. Minus 2 over secant. My derivative of secant is going to be secant x tan x. And then I go for the big finish. Y prime equals y times 1 over x plus cosine over sine. I could either write as cosine over sine, or most of the pros don't like to leave trig in the denominator, so I could rewrite cosine over sine as cotan x. Over here, my secants will cross out, and I'll get minus 2 tan x. And that is my answer. One of the #1 mistakes come test time is that kids forget to put the y out front because it doesn't serve any grandiose purpose. You're not doing any crazy arithmetic with it like you are with all these logs. Oftentimes it's neglected, but it really does need to be part of your answer. Alright, just to switch things up a little bit, this one looks like a pretty straightforward product rule, so I'm just going to use the product rule. Just because I have this cool new skill doesn't mean that that should be the only thing I use. So my u is going to be square root of x plus 3, and my v will be cosine x. My u prime is going to be 1 over 2 x plus 3 to the 1/2. My v prime will be negative sine. So to get this working, I do u prime, which is 1 over 2 x plus 3 to the 1/2, times regular v plus regular u times v prime. And that's my answer. Please note, if you're working with a friend and they choose to do logarithmic, it's going to look different, but it should be equivalent answers. To verify whether or not you guys agree, you can always take the person who did logarithmic, replace this equation for y, and then distribute it through. And then you should be looking at the same thing. It's one of the main reasons why college professors might ask you to replace that y, just to have consistency in all the different answer types. Alright, so then we get this guy. Remember, d dx means take the derivative of. So I'm basically just taking this equation and I want to find y prime. This is the first problem we've encountered where you cannot use quotient, product, chain to be able to approach this problem, even with a lot of time. That variable in the exponent is not anything that we've encountered thus far, which means the only way to tackle this problem is logarithmic differentiation. So I take my natural log of y. When I take the natural log of this side, remember my exponent comes out front, so I get root x ln of x. Take my derivative, 1 over y prime. Over here, this root x times ln of x actually requires a product rule. So even within the logarithmic, we might have to do a product rule. So my u is root x, my v is ln, u prime 1/2 x to the negative 1/2 v prime 1 over x. So I would say u prime times v plus regular u times v prime. And my derivative is going to be y times, alright, so I could call this ln of x over 2 root x, and I could call this root x over x. And that's my answer. Alright, so let's try this monstrosity. At this problem, we basically have an x squared times this. I could use logarithmic if I wanted to be able to work with that e, but this also kind of fits kind of nicely as just a product rule problem. Again, just because we have a cool skill does not mean we use it in every single problem. So we get to review our e's. If v equals e to the 5x plus 2, our derivative would be e to the 5x plus 2 times 5. And my y prime is going to equal u prime times v plus regular u times v prime. And that's my answer. Alright, last problem. So the big point of this problem is for you to recognize that if there's an ln already in the problem, that makes it a very bad time to use logarithmic differentiation. Logarithmic differentiation is not just derivatives with ln's. It's when you choose to put ln in the problem to try and make it easier. If there's already an ln in the problem, you don't need to introduce it. So I just simply start with my derivative, y prime. The derivative of ln of stuff is 1 over stuff. And then I follow that up with the derivative of that stuff. The derivative of x is just 1. The derivative of square root of more stuff would be 1 over 2, that square root. But then I got to follow that up with the derivative of the thing inside the square root, my inside-outside, 2x. And that's my solution. Alright, so you now know everything you need to know about logs, everything you need to know about e, and how you might want to introduce natural logs into a problem to make your arithmetic a little bit easier to handle.